Hello, everybody. Hello. Now we welcome everyone to our Peking University Engineering and Science Seminar Series. Now today we have a great honor and a privilege to have Francesco Bullo as our speaker. So before we formally get started, so I will briefly introduce Francesco. Francesco have a very long and glamorous CV, so I will keep it as short as possible. So Francesco is an old friend of this university. He visited us in person several times, and Francesco now is Professor Francesco Bullo. Now is a distinguished professor of mechanical engineering at the University of California, Santa Barbara. He graduated from the Caltech and also worked with UIUC. His research interests include contraction theory, network system, and distributed control. He is author and co-author of several books, monographs. And I want to mention one of it, the lectures of network systems. We use it as one of our books for our graduate class. It was very well written. And he is also the president of IEEE CSS and SIAG CSD chair. He's a fellow of the SME, IEEE, FX, CM, and many others. So today, the title of the talk is Contraction Theory for Control, Computation, and Dynamic Systems. So Francesco, thanks again. I will give you the rest of the time.
Thank you. Thank you, Zonkui. It is great to be here. Thank you for the kind invitation. It's really a pleasure to be here today. As you see, you can well, you don't see that, but let me mention that if you are following this presentation live, you can go to my website right now, search for my name, and there are these slides that are available for you to download. So if you want to follow the talk and be able to go back and forth and forward and ask more questions, you can get the PDF right now off of my website. So what is this contraction theory that I want to talk about to you today, and why should you care? So that's the purpose of my talk tonight. Before I proceed, let me thank the students, postdocs, and professors with whom I worked over the years. Veronica, Alexander, and Anton are current students working with me. Saber was a postdoc working with me. Anton, Giovanni, and John are professors who work with me on these topics. So I want to talk to you today about three different topics, and it's a little story, and it's in 3 chapters. So the first chapter is an overview, a glimpse into this field called contraction theory. I could say contraction theory for dynamical system, but it is also true that at the very heart of contraction theory is the Banach theorem, which if you look at with some attention, notice is actually dynamical system theory. It does talk about convergence of sequences to fixed points. And as you see in this picture, dynamical systems that are contracting have the property, have many strong properties. For example, have globally exponentially stable unique equilibrium point. And in red, you see these level sets, which are disks, which are unit balls as measured with respect to a norm. For example, here, this is the infinity norm. So it's a non-Euclidean norm in this particular case. And so the reason I like contraction theory as compared with Lyapunov's stability theory is that contraction theory is computationally friendly. Everything is measured in quantities, in numbers. The contraction rate is a positive number. We do not consider arbitrary Lyapunov function. We look at the Lyapunov functions defined by norms, and there's a lot of power that comes with that. And moreover, this notion of stability gives you numerous valuable robustness properties, which I will talk a little bit about. Contraction theory brings together not only Lyapunov stability theory, but also fixed point theory and the geometry of the metric spaces in which dynamical systems evolve. And so it's a refined tool that allows you to capture a number of properties in one shot. I would like to show you some applications of contraction theory that we've been trying to develop over the last few years. And I will talk to you a little bit about how does one understand recurrent and implicit neural networks. And the story here starts by observing that in the last decade, enormous progress has been made by studying deep learning and deep neural networks. But when one looks at biology, and so in deep learning, as you see in this picture, the fundamental idea is that multiple layers are combined together to execute an elaborate computation. But when one looks at biological systems and tries to imagine having input layer somewhere and an output somewhere else, for example, from sensors to motor functions in a creature, such as the C. elegans, then in fact, if you try to chase the flow of signals through this network, well, this is a recurrent network. And even just understanding the equilibrium input-output response, which would be described by an implicit neural network, that requires some more mathematics than the model on the left. So how do we understand well-posedness, stability? How do we compute the input-output responses, and how do we characterize the robustness of these networks? These are all answers that I will try to give you using contraction. And finally, I would like to also, the third chapter is a second application of this theory, and it has to do with studying time-varying optimization algorithms. Why should we be interested in solving optimization problems that vary with time? And I would like to do this by using continuous time dynamical systems. So I would like to design continuous time solvers that continuously optimize, drive the state of a system to the optimum of an optimization, to the minimum of, for example, of an optimization problem. And they do that in continuous time for time varying problems. Why would that be relevant? Well, so here is an example. You are considering a plant, but your plant is already being stabilized. It's stable and fast. Think of it as really essentially evolving on a different time scale than the optimizer, in such a way that the map from U to Y is essentially static. But of course, Y would depend not only about the input U, but it would also depend perhaps upon a disturbance W, which may be time varying. So now, in a classic, let's say QR quadratic, linear quadratic regulator problem, you would have a penalty on the control signal and on the state, or perhaps the output. So here you have two signals, a signal U and a signal Y, and you may well be interested in defining an optimization problem. Well, you penalize U and you penalize Y, and you wish to optimize U, which is to say, set up an optimization problem in U that will minimize a total cost consisting of a combined cost of U and Y. And so now it's natural to consider this problem in continuous time. It's natural to imagine that this problem depends upon time. And this area of designing, optimizing the behavior of dynamical system by designing dynamical systems, goes under the name of online time-varying optimization, optimization-based feedback control. But I will mention later the idea of using continuous time dynamics to optimize cost function is a classic one. It's been studied in computational neuroscience, in the design of analog circuits, in artificial neural networks, and so on and so forth. So that's right. So this is my outline for today. I would like to tell you a little bit about this new field that I find fascinating, of contractivity, and then I will apply that to neural networks and to time-varying convex optimization, and we will conclude with some future research. Right. So this is my introduction to my talk. All right. So let me talk to you about this contraction theory. And it all started with a wonderful PhD thesis by Stefan Banach in 1922. On the right is a statue in a garden in Warsaw, Poland, where Banach is discussing mathematics with his advisor, who found him and brought him into academia. Since then, there has been, of course, an enormity of work. Here are just a few references, which I think are sort of landmarks. In the 1950s, in the late 50s, German Dahlquist and Sergei Lodzinsky really brought this theory to continuous time dynamical systems. Important computational aspects were developed by Charlie Glissor, and the relevance of this theory for systems and control was highlighted in the late 90s in a paper by Jean-Jacques Slotin and Lohmiller. By now, you can find all sorts of references. I'll have a few more later. So how do I'm not going to cover the whole theory. Let me, of course, just show you a couple of basic things. So I'll work like this. So we'll work only on vector spaces for today. And I will consider the standard 2 norm, which you're all very familiar with, as well as 1 and infinity norms. As you well know, if you are on Rn and you have these norms, you can define something called induced matrix norms, right? For 1, 2, and infinity norms. And later on, please do not worry just yet about this. Later on, we'll do an extension. But for now, those are induced norms, and they're standard, well-known operations on matrices. So how do we study the stability, the robust stability or contractivity of a discrete time dynamical system? If you are living in Rn, you have a norm and you have an induced norm. I use the same symbol for the two on a matrix. Well, that's perfect. You need to introduce one concept, one notion, and that's the Lipschitz constant. There are two equivalent definition of Lipschitz constant, or more accurately, the first row is the integral definition, which always functions. And the second is an equivalent definition when the map F is differentiable or locally Lipschitz, so that it is differentiable almost everywhere. So now, the Lipschitz constant lip of F captures how much a variation in the input gets amplified in the output, right? So that's the constant L there, which you see. And you can either think about amplification or sensitivity. As you change two inputs, the outputs change, or you can perform equivalently, you can perform three operations. You calculate the Jacobian of F, number one, you take the induced norm of it, number two, and then you take the supremum over all states X. So you need to perform three operations: Jacobian, induced norm, supremum. That tells you the Lipschitz constant. If you have a scalar map, this is the same as taking the derivative, the absolute value of the derivative, and the supremum of the derivative. So that's the largest value taken by the absolute value of the derivative. That's the Lipschitz constant for a scalar map. If you have an affine map, and given a matrix A and a vector lowercase a, you can define an affine map F sub A of X, like that. And now you can compute its Lipschitz constant with respect to either the 2 norm or the infinity norm. And here I'm using weighted norm. So I'm introducing a positive definite matrix P or a positive vector eta of coefficients. And these are known to be weighted to an infinity norm, rather standard. And now you can ask yourself the question, what's the Lipschitz constant of this affine map F with respect to either the 2, P norm or the infinity, eta norm? And you compute the Jacobian, but this is a affine map, so the vector A goes away, and the Jacobian is just equal to the matrix A. And so now you take the induced norm, and then you take the supremum, but it doesn't depend upon X any longer. So it's just the induced norm, right? And up until here, this makes sense. And now I'm telling you another little bit of information. If you are familiar with norms and you play around with norms for a little bit of time, you can find out that the following equivalences hold. The 2 norm of a matrix is upper bounded by a constant lowercase l, if and only if the matrix A and the matrix P satisfies this LMI, this linear matrix inequality. And it's a little less well known, but it's still also known that in the infinity norm case, the condition reads, it becomes a linear program. You take this by absolute value of A, I mean to say absolute value of each entry of A. All right, and this is a linear program. So this should not be surprising, because this is the discrete time stability LMI. This is the discrete time stability LMI. In fact, more accurately here, it's not just stability. The stability LMI would be A transpose PA strictly less than P. This is a stability LMI in discrete time control theory. But here I am introducing L, and that's the contraction factor when L is less than 1, right? So here I'm actually beginning to move from just stability to contraction. And I would actually like to call this the contractivity LMI, because it's really telling you what's the rate, what's the factor in this case. So now, what does the Banach contraction theorem says for discrete time dynamical system? If you define, let's call rho, the Lipschitz constant of F, whenever that's less than 1. So then, when that's less than 1, then the map F is contracting. It's a discrete time strong contraction. The distance between trajectory decreases exponentially fast. And so if you observe here, the Y trajectory and the X trajectories, they're coming together exponentially fast. And now I'm going to animate for you the theorem. What does the theorem say? The theorem says that if you have this property, then there must exist an equilibrium point X star at the end of each trajectory, meaning to say, no matter where you start, all trajectories converge to X star. Does that make sense? This is my animation of the theorem, of the Banach contraction theorem in discrete time. Wonderful. So now, how do I go from discrete to continuous time? So now the answer is given. I just need to introduce one concept, and this concept is called the logarithmic norm. So this logarithmic norm, the definition here with this limit appears to be complicated. However, I would like to encourage you not to worry about the definition at all. Let's just say that it is an operation that is very similar to that of induced norm. It has a few differences. I'll show you the formulas in a slide, but it's an operation that is akin to the induced norm, and we'll review it. For example, it has two properties that are identical to those of the induced norm. It is subadditive, and it satisfies a positive scaling property. So now, it is well known that the induced, let me enlarge the picture on the left, that the induced norm of A is an upper bound on the spectral radius of A. And the spectral radius of A is the largest magnitude of all of the eigenvalues of A. So here you see, in this picture, you're seeing some eigenvalues, lambda 1 through all the way through lambda 6 of a matrix A. You're seeing the spectral disk in gray, which contains all of the eigenvalues. And then you're noticing that the induced norm of A is always an upper bound, right, on rho of A. And this gap here can be shrunk if you select your norm appropriately. So now my point is that this is relevant in discrete time, but if you work in continuous time, then the picture is a little different. But everything changes and it becomes the same again. So now the logarithmic norm of A is an upper bound on alpha of A, which is the spectral abscissa of A, which is the largest real part of A. And you now know that all eigenvalues are guaranteed to be to the left of it. And so, to cut a long story short, the induced log norm plays the same role in continuous time as the induced norm plays in discrete time. All right, and now you can see the full table. And, I would encourage you not to get scared by this because it's really quite straightforward. Just like there was a formula for the 2 induced norm, there is a formula for the 2 induced log norm. And just like there were formulas for 1 and infinity, there are formulas for 1 and infinity. And in fact, if we had time and I could just go over the details of this, you would see that, in fact, these formulas are, have some striking resemblances. All right, why did I do all of this? Because I am interested in studying contractivity in continuous time. And now, if you remember, this is the same as before, but I have induced log norm instead of induced norm. And just like before, I'm going to define a Lipschitz constant, which now I'm going to call the one-sided Lipschitz constant. I will write OS lip. And I'm going to skip the integral definition. I'm not going to worry about that for today's talk. Let me just say that just like before, you need to perform 3 operations. You need to compute the Jacobian. You need to take the log norm of the Jacobian, not the induced norm of the Jacobian, and you need to take the supremum over all states x. If the function is scalar, then now you take the supremum of the derivative, not of the absolute value of the derivative. So the one-sided Lipschitz constant is only an upper bound on the derivative. That's why it's called one-sided. And just like before, if you were to consider an affine map defined by a square matrix A, you would be able to quickly compute the one-sided Lipschitz constant of those maps, of that map, with respect to either the 2 or the infinity weighted norm. And just like before, if you do a little bit of matrix theory and you play around with the definition, you would be able to see that asking for the log norm of a matrix to be upper bounded is the same as asking for the matrix to satisfy another LMI. This LMI looks like the continuous time stability LMI in continuous time linear control theory. And again, I would like to call this the contractivity LMI, because it's not just saying that A transpose P plus PA is strictly less than 0, but it's actually telling you precisely how do I get the contraction rate. And that L needs to be negative if I want my system to be contracting. If it's positive, then potentially the system is expanding. So in contractivity, you don't just ask for something to be stable. You actually also characterize the rate and the factor. Everything has a number, has a name. It's not an app. There is not going to be any epsilon delta proofs in this talk. There is no epsilon delta in contraction theory. In contraction theory, everything is a number. It's very computational. And last comment about this slide is that in continuous time for the infinity norm, you get again a linear program, which is a little different from before, but that's fine. So now, just like before, the Banach contraction theorem tells you that if the one-sided Lipschitz constant satisfies the right property, in this case, it has to be negative. Let's use the symbol C in this case. Then again, then now you know again that any two trajectories come together, 1 and 2. And if you have, and the theorem animated for you is that there exists a point X star, and all trajectories converge to it from everywhere in space. Perfect. Now, using what I have said to you so far, you can construct tables of conditions to try to characterize contractivity with respect to arbitrary norms. And you can do that in different ways. You can do conditions. These are just the continuous time conditions. And there is an entire table of discrete time conditions, which I am not reporting. For example, with respect to the two norm, you can either ask for the log norm of the Jacobian to be upper bounded, or you can ask for the contractivity LMI to hold. And when I write an equation like this, I mean to say to hold for all x's. Or else, also possible is to write conditions, the integral condition, which, as I said to you, I'm not going to have the time to review today. And just like I do that with respect to the two norm, I can do that with respect to arbitrary norm. For example, in just a minute, I'll show you an example where I take the infinity log norm of a Jacobian. And these 9 conditions in this table are not new. Not all of them are new. A couple of them are new or recent, but they have been discovered over the century in an ad hoc manner. Different papers discover different formulas. And right now, today, I am making the point that these are all very closely related. These are all contractivity condition, either differential contractivity condition or integral contractivity condition with respect to either 1, 2, or infinity norms. Now, before I move on to the two application, actually, as a preparation for the two application, let me work out a couple of simple examples. Suppose, for example, that I start by considering a scalar function, and let's assume it is strongly convex. So then I can consider the continuous time gradient flow. Oh, and by the way, when you say strongly convex, it's strongly convex with respect to a parameter. Let's call that parameter mu. So it turns out that a simple proof, which I'm highlighting, but I'm not going to cover, shows you that you can easily verify the contractivity LMI. Starting from strong convexity, you can verify the contractivity LMI. And in bottom line, you can quickly establish that the gradient flow is infinitesimally contracting infinitesimal means in continuous time, is contracting in continuous time with respect to the two norm. And the contraction rate is exactly the same as the strong convexity parameter. So gradient flows for strongly convex functions are contracting. But also more general optimization problems give rise to contracting dynamical systems. For example, suppose you're trying to minimize a strongly convex function, but you subject that to a linear equality constraint. So here you have a strongly convex function, and you have a constraint matrix A, and let's introduce some numbers. So let's suppose that my function is not only strongly convex, but it's also strongly smooth. And what that means is that there are two parameters, mu mean and mu max, that upper bound and, well, that lower and upper bound the Hessian. And let's suppose that the matrix A is full row rank. So in other words, these constraints here are not redundant. And what that means is there exist two parameters, A mean, A max, upper and lower bounding the product A transpose. With that, in the literature, a standard approach to solving the primal dual, to solving this constraint optimization problem is to consider the primal dual gradient dynamics as defined here. Now, not so critical for you to know all the details, but the point again is that the primal dual gradient dynamics is contracting with respect to a two norm. This time it is a weighted two norm and with a given positive contraction rate. So the primal dual gradient is contracting. Here I have the formulas for P, which is the weight matrix that appears in the contraction rate. I need to introduce some parameter alpha, and I have an explicit formula for the contraction rate. This formula may appear to be complicated and a bit cumbersome, but in reality, there's actually very good reasons why it needs to be of this form. And I know that 518 looks like a weird number, but in fact, it's actually a pretty interesting and valuable estimate. Now, how does one prove that this is the correct approach? Again, this is all about establishing the contractivity LMI, which I am here writing for a matrix that arises from computing the Jacobian of my primal dual. So the Jacobian of the primal dual looks like this matrix, and the P matrix that I've just defined happens to satisfy the contractivity LMI. All right, as third example of contractivity, of contracting dynamics, let me consider a neural network, a recurrent neural network given in this equation. The recurrent neural network is described by a synaptic matrix A, an input matrix B with an input signal U. It's described by an activation function, capital Phi, which is a nonlinear function, but it's a diagonal function. So it takes, it applies to each scalar entry of the vector AX plus BU. And then it has a little bit of dissipation. And for the sake of simplicity, I'm just going to assume that the dissipation matrix is identity, but you can generalize this. So as activation functions here, I have two examples. But let me basically just assume that my activation function is slope constrained. So it has a minimum and maximum value of the derivative. Let's set those values to be 0 and 1. So this is applicable to ReLU and the hyperbolic tangent. Actually, the derivative is even less than 1. Everything can be scaled here. I'm putting 0 and 1, but the general treatment handles arbitrary values. And now, if you compute the Jacobian of the vector field and you look at the definition of the infinity log norm and you play around a little bit, you have to maximize it over all values of the state X, you will be able to prove that your recurrent neural network, and by the way, I'm calling it FR because because that's the language in the literature. So this firing rate recurrent neural network is contracting with respect to the infinity norm, provided that the infinity log norm of the synaptic matrix is less than 1. And if you look at the formula, what that really means is that the sum of all of the incoming edges or synaptic connections into node I, the sum of the absolute value of those entries has to be less than 1. Either that, or if you have a self loop, so if you have a self dissipation, perhaps AII could be negative, and if it's negative and large, then the sum of the incoming links can be positive and can be arbitrarily signed and large. In any case, this condition here has a simple graph theoretic interpretation in terms of the strength of the links coming into each neuron. I'm not going to go over the proof, but the proof literally is just a supremum of the log norm of the Jacobian. You just play with it. And you also need to keep in mind little properties about maximizing convex functions. As I mentioned to you earlier, the log norm satisfies subadditivity and positive homogeneity. What that means, it's convex. So you use these properties and you get the result you want. All right, we've done 3 examples. What have we done in this half an hour? We have reviewed the basic definition of contractility. Remember, we have seen 3 examples. I do not have the time, but I'm just going to state that systems that satisfy those conditions and are contracting have a large number of properties. Each such system has a unique, globally exponentially stable equilibrium point, and it comes with 2 natural Lyapunov functions. I'll skip it. It has each system like this comes with very nice robustness properties, which one of these properties I'll introduce in a second. Specifically, they satisfy input to state stability properties. I'm gonna go at that in a few minutes. If you apply a periodic input to a nonlinear system that is contracting, it turns out that the state evolves in a periodic way. You can interconnect contracting systems and give sufficient conditions for the interconnection to remain contracting. And I will show you that you can compute the equilibrium point in efficient computational manners. Because of all of these properties, I am referring to contraction theory as a robust, computationally friendly property. And my point as an engineer to you all is that as you study problems in in the sciences and in engineering, you want to search for contraction properties, and or you want to design systems to be contracting, because automatically, as you find or you design systems, you have all of those properties there. So now, I haven't had the time to do all of this. You can freely download from my website a book that I've recently been writing. With that, I am just going to move on to the two applications. All right. So what's stated in this slide, this is the first application I want to talk to you about, is that, and I already made this case, in most machine learning architectures are feed-forward. And yet, most biological neural networks are recurrent, meaning to say, there are, first of all, there is not even a notion of layers, but let us even suppose that I could partition all of these nodes in some slices. Then what happens? What happens is that there are lateral connections between neurons which belong to the same layer. There are feed-forward connections, but there are also feedback connections, right? So it's a much richer topology. And so how do you ensure that the dynamics of these systems are, well, at least in some regimes, are reproducible? If you perhaps in most cases, if you supply a certain stimulus to a biological neural networks, maybe it is true that you receive the same response from it. So how do you ensure you have reproducible behavior, which may mean that even if you apply a static stationary stimulus, you have the same equilibrium response? How do you guarantee that? How do you guarantee robustness in the face of uncertain stimuli and unknown, unmodeled dynamics? And how do you use these basic tools to then design learning models and design efficient computational tools and so on and so forth? And by the way, how do you study periodic evolutions of neural networks? So I have two pictures here. One is on the left is feed-forward, on the right is recurrent. And now I have mathematized this. I've removed all of the colors. On the left is, again, feed-forward, and on the right is recurrent. And recurrent, why do I say recurrent? Recurrent is typically an ordinary differential equation, and the equilibrium equation for the recurrent is sometimes called implicit. So the equation I've just highlighted here is an implicit equation because X appears both on the left and on the right-hand side. So I have an implicit neural network model. And I want to study these fixed point strategies or these implicit models. These are very common nowadays in data science. And in fact, I'm going to talk about fixed points and dynamics that reaches fixed points also in the second application, which is the third chapter of my story. But how do I make sense of this fixed point problem? Well, it turns out that the equilibrium response of that implicit neural network is exactly the fixed point equation or the equilibrium equation for the recurrent neural network example that I studied earlier for you, right? And so again, I mentioned 5 minutes ago that if the synaptic matrix has the property of having log norm less than 1, which means that, you have this condition on the way in which you combine all of the synaptic weights, all of the interconnections between neurons, then now I have two properties. One is that the ODE, so the recurrent neural network, is contracting with a given rate, and the implicit neural network is well-posed. Well-posed means that no matter what stimulus you select, no matter what is the bias vector V, there exists a unique solution to that implicit equation. And so if from a biological application or a machine learning application, you are given this type of fixed point problem or implicit problems, well, then my contractivity condition guarantees well-posedness, right? So now, well-posedness, the fact that there exists a unique solution to your problem, is a nice property, but that is not the only property I wanted. I actually want to compute this fixed point that Mr. Banach tells me exists, to which all trajectories converge. How do I compute that fixed point? It turns out that there is a nice little new theorem that I can place in front of your eyes. And it says the following. It's a forward-Euler theorem for contracting dynamics. Suppose you have a dynamical system, x dot equal to f of x. You can certainly define the forward Euler integration. I believe you may have been exposed to this in your first calculus class. You have an ordinary differential equation. You do Euler integration. You are at the point xk, you evaluate the vector field, multiply by a step size alpha, and that's your forward Euler, right? So now, the theorem here says the following. It says that contractivity is preserved. It says that in continuous time, your dynamics is contracting if and only if there exists a sufficiently small step size, actually even more accurate, there exists alpha star such that every alpha less than alpha star, right, ensures that the forward Euler discretization is contracting. And now I mean to say in discrete time, right? Contracting in continuous time, I discretize it, I get something automatically contracting in continuous time. And now I promised you not to use any epsilon or delta. In this talk, everything is explicit. And so what I meant by that is, imagine that for your map F, you know what the contraction rate is. You then also know what the Lipschitz constant is for that map F. You may well define the condition number. That's the ratio between the Lipschitz and the contraction rate. And it's guaranteed to be greater than 1. So now, in this theorem here, in these two results, I am providing you with the ranges for alpha such that ensure that the discretization is contracting. Not only that, but also I want to optimize the step size in such a way as to minimize the contraction factor of the discretization, so that I need to execute the smallest possible number of steps when I discretize and I want to compute a fixed point, right? So in other words, here, everything is relatively explicit. Now, I have a comment for you now here. This theorem here works for every norm. You give me any norm, this theorem works, and these expressions here are correct in general, right? If you have a specific norm, you may get a better estimate for the contraction factor, optimize it, and use a different step size, which is what I'm about to do. So I am back at my implicit neural network, which is a recently developed machine learning model. I have the continuous time version. And if I do the forward Euler of the recurrent continuous time version, I now get a new equation. This now is in discrete time. That's the forward Euler of the recurrent, also called the Krasnoselski-Mann iteration for the implicit. And so what that means, and now my contractivity condition tells you more than before. Not only the ODE is contracting, the static map is well posed, and the discrete time iteration is contracting in discrete time. And I can tell you what the rate is, and I can tell you what is the optimal step size. This formula for alpha star here is a little different from the one in the previous slide because I'm using knowledge of the fact that this is the infinity norm I am working with. Perfect. Now, I could spend more time now and tell you what additional consequences does contraction have and how do I write additional theorems that ensures that a model like this one is well behaved. Let me skip that. Let me only show you one additional property. In machine learning, there's a lot of interest in robustness. And what do I mean by that is that as you introduce inputs, which is corrupted by noise, which perhaps is not perfect, which has been quantized or whatever. If I have uncertainty in the input, how big a variation do I perceive at the output? if you give me a nominal picture and I perturb it, I quantize it, there is maybe an adversarial attack that changes the input, how much does the output change? And so now that's a Lipschitz constant question. The question is, what is the Lipschitz constant from the input to the output? Here, I didn't write the output equation, so let me just write the Lipschitz constant from the input to the state. It turns out that this technology or this theory of contraction theory that I've been exposing to you for the last 40 minutes even tells you the input-output Lipschitz constant. There is no epsilon, there is no delta. This is a formula. You give me the matrix B, you give me the matrix A, and I just calculate it. Closed formula. All right. We are now at the end of chapter 2 of my story. I have been talking about contraction theory, then I've shown to you one application to neural networks. And now I have another 10, maybe 15 minutes at most to do a second application. And I have already motivated my interest for time-varying optimization problems and solutions of them, not via discrete time iterations, but via continuous time iterations. Although you by now know that if I have a continuous time dynamical system and if I select sufficiently small step sizes, then it's going to work also in discrete time as a contraction. So, but for now, for the next few slides, I will work only in continuous time. So I have shown to you this picture before, right? We discussed it already. On the left here is a picture of a brain network. Now, the point is that there is really a lot of evidence that numerous biological circuits in our brains and in the brains of animals are in fact solving optimization problems, and they do so in continuous time. Classical work on continuous time solutions to linear and nonlinear program was all the way back to the 50s. In the 80s, Hopfield came up with his famous model in neural network, and Chua at Berkeley designed all sorts of analog circuits that were meant to solve optimization problems. Roger Brockett talked about dynamical systems that solve, that order lists and solve all sorts of matrix factorization problems in the early 90s and so on and so forth. Some of the ideas I am presenting today are inspired by some work about 10 years ago from Bolognani and Zampieri, and now there's been a lot of interest by Emiliano Dallanese, Florian Dorfler, and numerous others using these ideas for the purpose for control purposes. You know, this is sort of like an alternative version to model predictive control. So now, what's the story? First of all, I have already told you that if a function f is strongly convex, then minus the gradient is strongly contracting. And the point of this slide is to tell you that the connection is so strong that actually this is an if and only if. So there is a deep connection between convexity and contractivity. All right. And in fact, a strongly convex function has a unique minimum, and a strongly contracting vector field has a unique globally exponentially stable point, as we discussed. So now, broadly speaking, it is true that, you know, building also on 50 years of even more of research, that many optimization problem, convex optimization problem, can be solved using dynamical systems that are themselves contracting. The first example is the one that, now this is the third slide where I mentioned this, and that's the continuous time gradient descent. It's gradient descent because there's a minus sign, right? But there are many other examples. I have, let me skip forward, sorry. This is in poor order, my apologies. The second example, which we have already described, is the equality constrained strong convex function minimization, and you have the primal dual flow, right? Primal dual gradient descent. I've already discussed that. Now, more generally, if you have a constraint set X, which is typically closed, convex, and proper, then closed and convex, then you can consider something called the projected gradient dynamics. And or if you describe perhaps your constraint set, or more generally, you consider an optimization problem given by the sum of a strongly convex function f and an extended function g, which is CCP, close convex and proper, you can, there's an even more general approach that invokes something called the proximal operator. I'm not going to define it in this talk because I will be completely out of time. But nevertheless, suffices to say that, and even more, even when there is inequality, there are known in the literature contracting dynamics. So essentially what I'm mentioning right here is that for each of these 5 cases in the paper, you will find proofs and estimates for the contraction rate, for the Lipschitz constants, and so on and so forth. Right? So this is a catalog of continuous time contracting dynamics solving various kinds of convex optimization problems. What am I going to do with this? Well, as I mentioned to you, I am interested not in just solving a single static convex optimization problem, but in the literature, because of the control applications, it's interesting to consider the case where things are varying with time. Time appears, there's a disturbance W, or there are some system parameters that are changing, or maybe you're regulating the system to a set point, which itself is changing with time. So here, let us introduce a parameter theta, both in the optimization problem and in the dynamics. And we will think that theta is a function of time. That's the way in which I introduce time. So now, as you recall, when I just had x dot equal to f of x, I assumed typically that f was strongly contracting, was contracting in x with a rate c, which is strictly positive. Now, because I have a parameter theta, I not only assume strong contractivity with respect to x, but also I assume Lipschitzness with respect to the parameter. So basically, you have a function f of 2 variables. It is contracting with respect to 1. So the one-sided Lipschitz constant is negative with respect to 1. And it is Lipschitz with respect to the other. So this entire talk is about Lipschitz. I should have had a picture of Lipschitz, not of Banach, or maybe both pictures. So now, for systems that satisfy these 2 assumptions, contractivity and Lipschitzness, it turns out that if you consider any 2 different inputs, suppose you have a system and you subject the system to an input, ux, starting from an initial condition, x at time 0, and you consider a different initial condition, y0, and you subject the system to a different input, u sub y. For example, it could be that one input is equal to 0, so that's the system subject to no disturbance, and the second input is the disturbance. Or it could be that one system is one of the trajectory is the reference trajectory, and the other one is the actual trajectory followed by the system subject to noise, and so on and so forth. So you, because of contractivity, you automatically have an estimate of how the distance, let's call the distance, let's call it the error. So there is an error here, and you have an estimate on how the derivative with respect to time of the error evolves with time. And to cut the long story short, let me just rewrite that equation. That equation is essentially telling you that the error is decreasing exponentially fast with the rate c. If it wasn't for some kind of forcing L, which is proportional to delta, delta being the distance, the variation in the inputs. And this differential equation can be easily understood, right? And can be used in a number of ways. And the solution can be computed. Everything is quite explicit here. So, okay, bottom line, under these 2 assumptions, what can I say? I can say a number of useful things. I can say that if you were to consider an optimization problem where theta is constant, so for each fixed theta, of course, there exists a unique equilibrium, x star of theta. But x star of theta depends in a Lipschitz way upon the parameter theta. That's very important. So you have a parameter-dependent optimization problem but you automatically know that that dependency is Lipschitz, and you have an estimate for that Lipschitz constant, and the estimate is L over C, which makes a lot of sense because the larger is the constant with which theta appears, that's at the numerator, but then my Lipschitz constant for the equilibrium map diminishes, the larger is the contraction rate. Not only that, but more importantly, I can define now a new notion of error. My new error here is the distance between the actual trajectory of the system and the equilibrium trajectory. What does it mean, equilibrium trajectory? Well, theta is a function of time. So when the time evolves, the parameter is changing, the solution of the optimization problem is moving. So it's a trajectory, right? And I can estimate the distance using the norm between the actual trajectory and the equilibrium trajectory. And it is very desirable in control problems. You would want to track the equilibrium trajectory with a small error. And so here you have a formula which tells you what is the error doing. The error is doing something like this, right? Where here you have the derivative with respect to time of the parameter. If your parameters are moving slowly, the error will be small. Vice versa, if the parameters are moving quickly, the error will be large. All right, I'm almost at the end here. The point is that using all contraction theory that I've described for you in the first chapter of my talk, what do we know? We know many things. We know that if there is bounded input, so if the derivative of the parameter is bounded, the error is bounded. I even have these estimates, L over C squared, in terms of how much will be the final error be. If you give me an error if you give me a parameter that has bounded energy, the output will have bounded energy. If the input is vanishing, the error is vanishing. If the input is exponentially vanishing, the error is exponentially vanishing. And moreover, there's also the periodicity. If you were to apply a periodic input, or a periodic parameter theta, the solutions are periodic, which is quite remarkable in some applications. Here are two very simple simulations of an equality, of a time-dependent equality and inequality constraints. In red, you see in solid lines, you see the exact system trajectories, and in dashed lines, you see the trajectories of the optimum. I'm not going to spend too much time on this. Here is a plot illustrating our error estimates. So the error estimates are not, I didn't promise you fantastic error estimates. I just said that there are error estimates. So with the dashed line, with the dashed line is the error estimate from the theorem, whereas here, down here, this is the actual error. As you see, we are, I would argue, the same order of magnitude, but not super tight. So some more work can be done here to optimize these estimates. And finally, allow me to conclude, my time is up. I have shown to you, maybe I'll skip this slide and I'll give you the total summary. Right, I have given for you, I've studied contraction theory, and I have, my story had 3 chapters. Then I talked to you about recurrent implicit neural networks. I talked about time varying optimization and its application to control problem. Essentially, in this table here is a comparison between Lyapunov theory and contraction theory. So contraction theory is a Lyapunov theory which is robust and computational. I mean, for example, but it's even more than Lyapunov theory, because, for example, if you look at your standard Lyapunov stability theorem, you start by saying, given an equilibrium, is it stable? But in contraction theory, you don't have to say that. The existence of the equilibrium is implied by the contractivity condition. And the contractivity condition gives you a way of computing it. And in the Lyapunov theorem, you have to look for an arbitrary Lyapunov function. In contraction theory, the 2 Lyapunov functions are x minus x star and the norm of f of x. So x star is the equilibrium, and these are 2 functions. Let's just call them v1 of x and V2 of X. So you're automatically given the Lyapunov functions if you can verify the contractivity conditions. And then in Lyapunov stability theory, a lot of modern nonlinear stability analysis based upon Lyapunov stability theory is based upon the notion of input to state stability, ISS. And for those of you familiar, there are class KL functions, class K functions, class L functions, and so on and so forth. But in contraction theory, it's different. Everything is fully explicit. It's C, the contraction rate, L, the Lipschitz constant, and how they come together in various ways. So everything is very explicit. All right. And with that, I am going to conclude my talk. Thank you for your attention. It's 1 minute past the hour. I would be delighted to receive any questions. These slides are on my website right now. There are some future directions, and these DOI links should all work. And so you hopefully can download. You can download the book for free. There are YouTube videos of me teaching contraction theory, and so on and so forth. So thank you all for your attention.
Okay, thank you.